And with that, we'll begin with our first speaker, which is Etienne Bachelet, who will discuss the synergies between Roman and other major surveys and their potential for microlensing science. And if I could ask the first speaker, please share your screen.
Thanks, Rach. Does that work?
Looks good.
Okay. Ready when you are.
Go ahead.
Okay.
Please.
So thank you, Rach. Yeah, I'm Etienne Bachelet. I'm a postdoc that recently moved from Las Cambres Observatory to the Institute of Astrophysics of Paris. And now, today I'm going to discuss about the potential synergy between Roman and other survey. And I will focus on the microlensing science. So I would like to thank the committee to invite me to give this talk today. So to summarize the Roman microlensing survey, it is one of the primary missions of the Roman spacecraft, and it will consist of a 5-year of 70-day windows survey toward the galactic bulge. And we expect that this survey will be able to detect 1,400 cold planets, and it will be sensitive to whole host type from M-dwarf to stellar remnants, and it should detect also hundreds of free-floating planets. On the left, I display the distribution of known planet in mass versus semi-major axis, and we can see on left that radial velocity and transit method, especially the Kepler mission, has given us a lot of information about what we call hot planets, or planets that are orbiting between at less than 1 AU, and we have learned a lot about this planetary system. And in blue, you can see the distribution of the potential planets that will be detected by Roman. They are simulation, and we can see that Roman is much sensitive to a planet beyond the snow line at more than 1 AU of the system. And so basically, when Roman will have finished its census, we're going to have a very good knowledge of all the planet demographics in all the parameter space. So on right, I display the massive field of view of Roman, which is roughly 100 times the size of Hubble. To give a quick introduction to microlensing. So microlensing is a phenomena that which is a gravitational lensing, and it occurs when a lens crosses the line of sight between the Earth and a distant source. And as soon as the alignment is sufficiently small, the gravitational field of the lens will bend the light coming from the source and create several images of the source. And when the lens leaves the line of sight, the phenomenon stops. So it's a transient event. And in case of microlensing, the lenses are generally of few solar mass, and therefore the Einstein ring and the separation between images are order of milliarcs, and therefore we can't observe the image directly. So the only phenomena that we can observe is a brightening of the source flux, and we obtain this kind of typical light curve that you can see on the right, when the flux of the source getting brighter, when the lens getting closer to the line of sight, and the flux decrease when the lens leaves the line of sight. And if by any luck you have a planet orbiting the lens, then the planet itself gonna act as a small lens. It's gonna create its own little magnifications. This is what we call planetary anomaly, and you can see here it's called the blip. And one information we can have from microlensing events is directly linked to the duration of the event, because it's proportional to the square root of the mass of the lens. So for typical lens of a few solar mass, the event duration is from 10 days to 100 days, and for the most massive, we can go to 200 or 300 days. And the same apply for the planetary anomaly duration. A Earth mass planet will create a duration of a few hours, while a Jupiter mass planet will create an anomaly of 1 or 2 days, let's say. So one of the challenges we have in microlensing is to measure the mass and distance of the lens, because they are not directly observable. So to constrain the mass of the system, we need to observe extra parameters, and one of them is the microlensing parallax, and we can obtain it if we observe the same event from two locations sufficiently separated. So here I display the case of Earth and Spitzer observation that observing the same event, and we can see directly the effect on the light curve seen by both observatory. We see a shift in time and shift in magnification, and by measuring the shifts that give a direct measurement of the parallax, and that give a first constraint on the mass and distance of the lensing system. Here is a second example by Street et al. In 2016. The light curve in black and color are a ground-based observatory, while the blue one is from Spitzer, and again the shift both in time and magnification give us direct measurement of the parallax. And for this case, we also can see on the inset that the planetary anomaly actually display finite source effect, and this effect provide us a second mass distance relation for this precise event. The mass and distance of the lens were very well known very precisely. So this has been done routinely in the history of microlensing, as you can see a list of publication here. Another method to measure the mass is to use high resolution imaging prior or posterior to the event peak. So here, for example, I display a study by Bando et al. In 2020, where they observe with Keck the event location 6 years after the event MOA 2013-20. And at this time, so 6 years after the peak, we can clearly see the separation between the lens and the source. So this can give us two measurements. One is the proper motion between the source and the lens, the relative proper motion, sorry. And the second one is, of course, the lens flux. So if we use these two constraints in our modeling process, we obtain the red distribution on the left diagram. So you can compare the mass and distance distribution with and without the constraint. Blue is without and red is with the Keck constraint, and this measurement offers us a very precise way to estimate the planet mass. So here is a similar example by Aparna Bhattacharya et al. So in their case, they didn't observe directly a separation between the lens and the source, but instead they observe the lens and source combination at the same time with Keck and HST in 3-band Keck, Keck-K, HST-I, and V. And because the lens and the source have different color and brightness, then the lens centroid is shifted differently in the different bands. And if you use a model of double PSF, you can reconstruct the proper motion and also the brightness of the lens. And again, if you use this constraint in your modeling, you will be able to much better constrain your planet mass. So the Roman microlensing survey will consist of 7 fields of view, as displayed on the bottom right, for a total field of view of 2 degrees square. The main filter will be the W146. It's a wide filter with a 0 point of about 27 mag. The cadence will be 15 minutes. Every couple of hours, there will be a second filter to obtain color information on the event and the field, which is very important for us. The overall mission, the primary mission, will consist of 6 windows of 72 days of observation for a total 40,000 exposure in the main filter, and the light curve duration will be about a year after the 5 years. So here are example of the light curve we can expect. There are simulations from Penny et al. And Samson et al. So on left, you see a typical planetary anomaly event where the planetary anomaly here is due to a moon moon mass planet at 5 AU, and you can see it creates a very small duration anomaly of about 1 hour 2. And on right, you can see 2 free-floating planet event. The top one is due to a 0.1 Earth mass, while the second one is a 0.6 Earth mass. And we can see from the simulations that Roman will be very sensitive to this kind of event, and we will be able to characterize them well. So in summary, this program will detect more than 30,000 events with 1,400 planets with 200 less than 3 Earth mass. We should detect, here I put 300 free-floating planets, but of course, the exact population of free-floating planets in Milky Way is not very well known. We also be able to characterize thousands of binary lenses and hundreds of stellar remnants. And ultimately, this will place strong constraint on the mass function of the phaeton component of the Milky Way. There will be also a lot of auxiliary science that can be done. I will not discuss that today. And one thing which is very interesting is that all data will be almost immediately public. So now I will come to potential synergies. So today I'm going to discuss mainly about Euclid and LSST at Vera Rubin synergies. That's why it's so big. But as Benjamin discussed yesterday, there is, of course, many more, and especially with JWST, Gaia, 30-meter class telescopes such as ELT. But today my main focus will be Euclid and Rubin Observatory. So one thing which is interesting to recap is that all of these 3 missions have gigantic field of view. Here I display in blue the Roman Microlensing field, the 7 fields that is about 2 degrees square. And we can see that in 4 Euclid pointing, we are able to cover the area, while one shot of Rubin should be able to cover the entire area. So here I display, I summarize quickly the characteristic of each mission. And what we can see is there is a lot of complementarity in these missions. The first one is in wavelengths. Both Roman and Euclid will observe in optical and infrared, and Rubin will be more focused to optical, but the complementarity of all of the filters will be very precious for a lot of science. You can think, for example, of the study of star-forming region, where this kind of complementary filter is very important. Also, all of the missions have different limit mag. So again, this is complementary because one transient can be found in one survey, and the location can be used in another one to try to do force photometry, for example, and that can give us important constraints at different time. Also, the location of this mission is different. Roman and Euclid will probably have similar orbit around the L2 Lissajous orbit, but Rubin will be on Earth. So as I will show later, that can play a role. And also Euclid and Rubin first light will be much earlier than Roman. And again, that can provide us some information and time complementarity. So here, for example, I display a simulated light curve by Street et al. That show a planetary anomaly that can be observed by Roman in the future. And we can see here the 3 windows of 70 days. So while the planetary anomaly is very well covered by WFIRST, there is some part of the light curve that are missing data. And in fact, if this field are observed by Rubin, for example, the model of this the model will be much better constrained in this region where we don't have any data. Now I will present the work that I lead with a team since 2 or 3 years that studies the potential of a Euclid-Roman joint survey. Our first idea is to use the fact that Euclid will be launched much earlier than Roman to take a snapshot of Roman field using Euclid. So this early survey consists of 4 pointing and destroying image for a total of about 7 hours. And to study the potential of such survey, we decided to simulate image from both from Roman and Euclid. So you can see on left, it's a typical galactic bulge image of Roman, where we injected some microlensing event inside. And on right, you have the same field of view simulated several years prior to Roman observation. So at this time, most of the source and lens are not are resolved. So here we make a zoom on a microlensing event. So on the image on left, on Roman, the event is ongoing. So it's hard to see, but the lens and the source is currently superposed. And on right, the source and lens are actually resolved. Yeah, I know it's hard to see just by eye like this, but if you plot ISO phot contour, you clearly see that on the Euclid image, the lens and the source are very well resolved. And using this information, you can, as I discussed previously, measure the relative proper motion and the lens flux. So we did an analysis on a couple of events, and we found that just using the Euclid image, we are able to recover 30% of the relative proper motion at better than 1 millisecond per year. And we were able to reconstruct the source and lens flux at for 40% of event with better than 0.1 mag. And of course, if you use this constraint on microlensing event of Roman, you directly get a mass and distance measurement for left fraction of Roman event just after the first year of Roman. The second survey we have in mind is to use the potential Euclid extended mission to run a simultaneous Euclid and Roman survey of microlensing field. And the idea is to be able to measure the parallax of event, especially down to the free-floating planet regime. Here is a free-floating planet observed by Ground-Based Observatory, published by Mrose et al. In 2019. And the authors were not able to distinguish the two scenarios between a Jupiter mass in the disk or Saturn mass in the bulge. And the main reason is they were lacking one of the mass-distance relation. But in 2019, Matthew Penny and I, we make a study of the potential of this joint survey to detect the parallax for free-floating planet event. And as you can see on the top right figures, if you use Roman and Euclid, you constrain the parallax for most of the event, at least down to 1 Jupiter mass. And of course, you need a minimum distance between the two spacecraft around L2. So this is what you can see on the left. We found that you need at least 100,000 kilometers between the two to be able to constrain the parallax of the events. So here is 3 examples of free-floating planets events seen by Roman and Euclid. On left, it's a Jupiter mass free-floating planet, while in the middle, it's a Neptune mass free-floating planet, and on right, it's a Earth mass. And we can see for some of them events that the shifts are sufficient between the two to be able to measure the parallax efficiently. So to have a better understanding, we simulate billions of events, and we apply different criterion to see if we are first able to detect the microlensing event. This is basically a signal to noise criterion. We also make a criterion to know if the parallax is detected at 5 sigma or not. And as well, we decided to see if final source effects were measured or not. So we used 2 distributions for free-floating planets. The first one is from Sumi et al. It consists of 2 free-floating planets per main sequence star in the galaxy. That is a delta mass function at Jupiter. And the second one is a 10 free-floating planet of 1 Earth mass per main sequence star from Mrose et al. And we can see in both cases that the parallax is almost always detected for all events. 85% of them show parallax effects we can detect the parallax between the two spacecraft. And the second one is about 20 free-floating planets per year show both final source effect and parallax. So for this one, we're going to have a direct measurement of the mass and distance, while for those with only parallax, we just have only one constraint. But this gives us already a lot of information about the distribution along the line of sight towards the bulge. Here is another example of parallax measurement using Roman and Rubin. So you can see for this event of duration of a few hours that if you are lucky and Rubin observes this field at the same time, you can have the parallax measurement from Rubin as well. And here also you can have a complementary bounds that give us info about the exact nature of the system. And now I will
just over 4 minutes.
Yeah, okay, thank you. I will conclude by moving from microlensing to all science case and show, for example, this work from Jane et al. In 2015 that show on the bottom left figures that the combined data do a much better work than individual mission to constrain, for example, the sigma 8 parameter, which is the galaxy clustering cosmological parameter. Or also the total mass of neutrino is also much better constrained using all dataset altogether. This is also the case for the estimation of the photometric redshift, as you can see on top right. And one of the main reasons for this is by combining all of the data set containing a lot of systematics that are individual to all mission. You can see also work by Rhodes, Shari, and Sapak that displays similar results. And I will end by highlighting the work that we recently published to arXiv, which is a Rubin Euclid-derived data products. In this kind of white paper, we discuss a lot of that science case that will benefit from not only join the data products at the end, but really combine the data product to extract the most of each mission. So that concern a lot of science in extragalactic and both galactic science. And inside this paper, we also discuss the nature of this derived data product. What are they? How each of them impact different science. For example, we quickly realized that building joint catalogs of both mission is beneficial for almost all science. Similar for proper motion, etc., for example. And we also discuss what are the challenges to obtain this kind of data products. So I really think we should start to think of something similar using the Roman data and all of the survey. So I will stop here and take any questions. Thank you.
Well, thank you very much, Etienne, for an excellent talk to kick off today's session. And just as a reminder to everyone who just joined, firstly, welcome. And if you have questions for Etienne or any of our speakers, please put them in either the Zoom chat or in the Slack channel, which is the channel session 4. So I'll be monitoring both of those. And I see it's early morning, at least here in California. So it's a little quiet on the Slack channels for the moment. So I'm going to take the chair's privilege and jump in with my own question. And Etienne, I was reminded as you were speaking that in addition to the Roman mission due to be launched, of course, we have recently had the JWST launch. So have you made any consideration of what JWST could provide in synergy with the discoveries made by Rubin and Roman?
Yeah, so I start to think, I start to study what can bring GWST for microlensing, for example, and for sure it will be very interesting to study how much we can get by high resolution imaging GWST, similar to what we do with cake, for example. I will say it's probably I mean, we're gonna have to wait only 1 year to have a similar result with GWST. But yeah, this is a formidable machine, of course, to use for science.
Yeah, it'll be fantastic to be able to get that mass measurement without having to wait a decade to make the high resolution imaging.
Yeah.
I see a question from Valerio Boza in the chat. I remember that Euclid has some charge transfer efficiency issues. Have they been solved, and would they impact the astrometry significantly?
So I'm not too aware about if there is problem with the charge efficiency, and I don't know how this could impact the study we made. So I'm sorry, I can't really reply to this function, to this question, sorry. But from the discussion we had in our group with people from Euclid, they say it should have not a major impact on our astrometric solution.
Thank you. And just to point out, I think there are later sessions this meeting, Valerio, where the instrumental issues may be a good place to discuss that question. Question from Will Dawson. You explored how the different filters can complement one another in resolving the lens and source. Have you explored how achromaticity in the lensing signal might be used even if you can't resolve the source and lens?
No, I didn't explore that, and it's a good idea. So we'll be happy to jump on that when I found some time. Thank you.
Thanks for both of those questions. Does anyone else have anything they want to post?
There are a couple questions in the Slack chat.
Okay, I'm not seeing those.
Under Etienne's thread there. Session 4.
I was looking at the session 4 thread.
Yeah, it's under the Bachelet thread. I can read them. I can read them for you.
Sorry, my bad. Yes, I should
That's
have been
okay.
looking at the other communication channel. Okay, thank you. From Rachel Aitken, how will time be allocated in an extended mission for Euclid?
It's a good question. I don't know yet. I think Isa and is thinking about is looking to reply to this question, but I don't know yet how the process will work.
Thank you. And I think we have time for one quick question from Samuel Johnson. What was the survey strategy assumed for Roman in the Roman Euclid FFP mass parallax measurement predictions, or was that for the prime Roman mission?
So we assume a standard Roman mission, 15-minute cadence, etc. It just we only consider 30 days windows because we know that the constraint, the observing constraint of Euclid will not allow more than 30-day observation towards the galactic center. So it's only half of the Roman window. So this is the only assumption we changed to the Roman design.
Okay. Thank you, Etienne, very much. And thanks everybody for some great questions. That was a terrific talk to get the session started with.